Hi everyone, this is Professor Fernandez, and in this video we're going to talk about Module 2 in Lesson 12. So we are talking here about double integrals in polar coordinates. In the previous video we had talked about, I'll scroll up a little bit here so you can see the markings. We had talked about polar coordinates, a little review of that, and also introduced spherical coordinates. So I had promised in that video that we were going to do double and triple integrals in polar and spherical coordinates in future videos. And that we would also talk about the volume and area elements. So this is the first video in that series, and we will focus on double integrals. So I've started here with the definition that I want to go through, but rather than go through the first part of it, which is the more general part, I just want to pick up the story where we left off in the previous video, talking about polar rectangles. So as a very quick review, I'm going to scroll up a little bit here. Remember that we were thinking in the previous video about R being, well, first of all, we were talking about polar coordinates, where the first coordinate is the R value, the second one is the theta value. And we were thinking in the previous video about some R that is perhaps constant. So this might be like R equals A, and then at a certain theta value, and then same R equals A up here at another theta value, theta 2, and then that kind of generates, as theta varies, this arc here. And then we thought about, well, what if R gets a little bit bigger? So now we're looking at R being R equals B. And same deal over here. I sweep it to R equals B. And then that generates some other arc. And then we look at this enclosure by these two arcs and then these two line segments, and that's what we thought about in the previous video as these polar rectangles. So there you can see my original marking from the previous video. So again, that's defined by theta taking on certain values. In this figure I've called them theta 1 and theta 2, and R taking on certain values. In this figure I've called them A and B. So in the definition, I'm using something very similar. However, I'm using R between A and B. That's the same thing, but I'm using alpha and beta as theta 1 and theta 2. So those are our polar rectangles. So suppose we are trying to integrate a continuous function defined on one of these polar rectangles, R. So that's what we've been doing a lot of in this unit 3 in the course. If we want to do this in polar coordinates, then we also talked in the previous video about how x was equal to r cosine theta and y was equal to r sine theta. So it makes sense that if I'm going to convert the coordinate system to polar coordinates, everywhere I see an x and a y, including in the integrand, I would put in r cosine theta and r sine theta respectively. So this part should make sense. We're converting the integrand in terms of x's and y's to the integrand in terms of r's and thetas. This is what I mentioned here. This is the polar area element. This is the conversion of dA, which is our dx dy. So I'll show you why that is what it is in a minute. But notice again that the limits for r here, because we're going from a to b, are just a to b. And then limits for theta, because we're going from alpha to beta, are alpha to beta. So really the only thing left unexplained in this right-hand side, double integral, is this area element. So let's talk about that. So I have pre-drawn some diagrams here to make it a little easier for us to talk about them. On the left over here, I have drawn what is very similar to what I drew a minute ago, sweeping out an arc of radius r, and through an angle delta theta. What I want to remind you here is that remember back from geometry, if I have an arc of a circle that I sweep out with some radius r, and the arc I sweep out for some central angle theta, then the distance here, s, the arc length, is equal to r times theta. So that's a little fact that I want you to remember from geometry. So that's why I'm using it over here to show you that the distance of this arc, this red arc here that I've kind of put in blue and black now, is r delta theta. So why is that important? Because now I'm going to go over to this figure on the right. And I'm going to say, rather than sweeping out just, or going just a distance r from the origin, what if I go a little bit more, delta r here? And then I sweep out my arc again, right? Then I create this polar rectangle that we've been talking about in this previous module and now here also. And what I want to do now is I want to find the area of this polar rectangle. I'm going to call that delta A. Well, the area of that polar rectangle is approximately the area of a regular quote-unquote rectangle in a Cartesian coordinate system, length times width. And this polar rectangle is about r delta theta wide and delta r long. So that's what I've put over here, r delta theta times delta r, which multiplies out to what starts looking familiar, r delta theta. And then certainly as delta r and delta theta tend to 0, we make them infinitesimal changes in r and theta. That's where this area element r dr d theta, which is up here in the double integral, comes from. So again, it's about thinking of a generalization as best we can of what a Cartesian area element is, dx dy. That's literally just an infinitesimal rectangle. In the polar coordinate system, our rectangles become these polar rectangles, these kind of polar wedges. And through this very simple illustration that I've drawn, should be able to convince yourself that indeed the area element dx dy converts to what is now r dr d theta. Great, so that explains the only portion of this double integral on the right that was left unexplained. Now let me go up to the rest of the definition. So what if things are more general? All right, so instead of a polar rectangle like we've been talking about here, what if I look at a region where I don't have these nice circular arcs bounding my region of integration? What if I have, I relax the fact that they're circular and make them a little wavy like that? Maybe I keep the theta nature of it. Okay, so now I have some curve here that's r equals some function of theta. And then I have some curve over here that's r equals some other function of theta. So that is the motivation behind this first part of the definition. So again, we're going to assume that f is continuous on whether it's a polar rectangle or one of these more general regions, right? So let's take a look at this definition. We're still taking theta to go from alpha to beta, but now we're allowing, again, like we just saw, the bounds for r to be a function of theta, not just to be constant numbers. Where again, we're assuming all the functions involved are continuous. So in that case, much of the double integral remains unchanged. Theta goes from alpha to beta. We replace x and y by r cosine and r sine theta. And then the area element we just talked about is r dr d theta. The change, of course, is that the bounds for r are now h1 to h2, as functions of theta. So you can see how this portion of the definition generalizes what's going on down here. So what I want to show you next is a couple of examples so that we can talk about graphing in polar coordinates, which is something that I had mentioned in the previous video, and then also certainly integrating now in polar coordinates. So I'm going to remove all of this so we can talk about this example and also review again how to graph in polar coordinates. So let's see what this says. So let R be the region defined in the upper half plane, okay, bounded by these two circles. Evaluate this double integral. Great. So the first thing we usually do for double integrals is we sketch our region. So let's do that. So I already know it's in the upper half plane, so there's not going to be anything down here that I need to sketch. And then these are circles, concentric circles, centered at the origin. First one has radius 1, the second one has radius 2, and it's upper half plane. So I'm just going to draw the upper semicircles. There's the first one, there's the second one. And then it's bounded by this region R, by the circles, and in the upper half plane. So basically, this is my region that I'm integrating over. You can see that this is effectively like a version of these polar rectangles that I keep drawing. The difference is that this is just a longer polar rectangle. It goes all the way to one of the from one of the axes to back to the axis again. So now that I've drawn my region, I'm going to start the process of converting the integral over to polar coordinates. I'll do the easy parts first. So we'll have to figure out the bounds in a minute, and we'll have to figure out the function in a minute. So the easiest part is the area elements. So we just discussed how dA becomes r dr d theta. And that's something that you can always count on. So you won't have to worry about that becoming something else. If you're working with a double integral in polar coordinates, that's your area element. And then now I have to think a little bit about the bounds for theta and r, or maybe I could go over here and convert the function. It really doesn't matter at this point. It's sort of a personal preference. So I'm going to convert the function because that's more formulaic. You literally just substitute r cosine theta for x. So I get 3r cosine theta. And you substitute r sine theta for y. So I get plus 4r squared sine squared theta. Great. And then now I am going to worry about the bounds. So I need to think about this region in terms of polar coordinates. And one thing I noticed right away is that the region is bounded if I draw a line from the origin at some random theta value. The region is bounded by r equals 1. In other words, all of these points on this first circle are a distance 1 from the origin. And the points up here are r equals 2. All of these points are a distance 2 away from the origin. So those are actually my r bounds. So that means that r goes from 1 to 2. And then theta, remember that theta is measured from the positive x-axis. So when I start over here in the region, I'm at theta equals 0. And then I sweep out this region, I get to here, I'm at pi over 2. I keep sweeping it out, I get to here, I'm at pi. So theta here goes from 0 to pi. All right, so now I've converted the integral over to a polar integral, and everything is in terms of r and theta. Great. So what I'm going to do now is do a little bit more algebraic simplification to remind you of some trig identities that you will need once you do more of these integrals. I won't spend too much time actually working out the integral because I want to practice the new skills, which is reviewing how to graph in polar coordinates, and certainly sketching regions and using the area element in polar coordinates. Okay, so I'm going to multiply in this r to give me 3r squared cosine of theta plus 4r cubed sine squared theta dr d theta. So at this point I can integrate the r, so that is going to give me a 3r squared integrates to r cubed cosine theta. And then over here I get r cubed integrates to r to the 4th over 4. So that 4 over there cancels. And I get this from r equals 1 to r equals 2 d theta. Great, so I'm going to just write out for you, skip one step so that we can keep talking about these special new skills that we're learning. So I'm going to just, this would be the fundamental theorem of calculus step. Substitute in r equals 2 here and here, and then subtract, substituting r equals 1 there and there. After you simplify things a little bit, you will get 7 cosine theta plus 15 sine squared. So that's one thing you can check, d theta. And then here comes what I had mentioned, that this is a great time to review some of these trig identities. So integrating cosine is not bad with respect to theta. So we just get sine theta. Integrating sine squared, though, is a little bit slightly more involved. The easiest and best way to do this is to convert this using a trig identity. So you might remember that sine squared is 1 minus cosine squared theta, but that's not really going to help. It'll convert the integral of sine squared to the integral of cosine squared. Instead, there's another trig identity, which is very useful. And this is going back to calculus 2 when you were integrating sines and cosines and powers of them. And that trig identity is 1 minus cosine of 2 theta all over 2. So if we use that trig identity here, we can convert the integral into this new one. So plus 15 over 2 times 1 minus cosine of 2 theta, d theta. Excuse me. And at this point, we have three separate terms in our integral. We have 7 cosine theta. If we multiply out this 15 halves, we're going to have 15 halves. And then we'll have minus 15 halves cosine of 2 theta. So 1, 2, 3 terms. And now we're back to calculus 1. So we can integrate each one of these separately, and we can use our fundamental theorem to evaluate them from 0 to 7. I will ask you to fill in the steps here and show that the final answer you get is 15 pi over 2. Okay, so as usual with any double integral, if the integrand is always positive, we can interpret this as the volume under the graph of f, the integrand, and with the bounds being the region R. In this case, this polar rectangle. So x equals r cosine theta here, and there are some places where x is negative, so I'm not going to interpret this as a volume or visualize the function for you. Again, I'm more interested in practicing these other skills. But just to say that because x is negative, this would be a net signed volume. So there may be portions where the volume is subtracted, so to speak. Nonetheless, this number does have some geometric significance if that helps to understand these concepts. Great, so we have done the first example, and then let's go and see a different example where now we really are going to calculate a volume. And let's visualize this a little bit. So first, this example says find the volume of the solid that lies under this paraboloid, above the xy plane, and then inside the cylinder. Okay, so there's a lot going on here. So first, I'm going to draw the region as best we can. First, I have a paraboloid. So this is a familiar shape that we've drawn several times now in the course. And then I have the xy plane, so I'm not thinking of anything below the xy plane. And then I have this cylinder. So to get a really good sense of what this cylinder looks like, I should write it in a way that is a standard form. So I'm going to complete the square here by adding half of 2 squared and subtracting half of 2 squared. That's my complete the square step. And then this collapses to x minus 1 squared minus 1 plus y squared equals 0. And then I can rewrite this as this. Great. So we recognize this as the equation of a circle with center 1, 0 right there of radius 1. So we can draw a circle here. And then remember that this is effectively a generalized cylinder when we're drawing it in R3. So we have this cylinder that goes up, and it also goes below the xy plane. But I am told in this problem that I only want to consider the region of integration to be above the solid, I should say, above the xy plane. So I'm just going to draw that. And then you can see this is a little hard to picture, so I'll draw you a different picture because the paraboloid here goes into the cylinder. It actually penetrates into the cylinder. So I'm going to draw you a slightly different view of this. We have a little bit of the cylinder inside the paraboloid and a little bit outside the paraboloid. And then the cylinder, the paraboloid kind of cuts it that way. So you can see that it's a little harder to visualize, but the portion of the solid, I should say, that we're trying to visualize lies under the paraboloid, above the xy plane, and inside the cylinder. So it's this region that is inside the cylinder over here and under the paraboloid. So it's kind of all this stuff. Okay, so how are we going to find the volume of this region? Well, so the first thing to remember is that we are finding the volume that is under the paraboloid. So this is our function. our f of xy function. So that's going to be our integrand. And then we're going to find the region of integration by figuring out, just from this picture, what the region D is. You can see as I've drawn it here that the point at the origin is kind of where the solid starts. All this other stuff over here is fair game for the cylinder, and intersects the paraboloid. If I kept drawing the paraboloid here, it would intersect the paraboloid right there at that point, as I've shown over here. So I'm going to draw this region of integration then. This is the cylinder itself, and we know that it's a circle of radius 1, centered at 1. So this is our region of integration. And at this point, you might be thinking, how do I convert all of this to polar coordinates? So let's set up what we know so far. So we are trying to find the volume under the paraboloid, which is x squared plus y squared. I'm just going to write it dA for now. And then we're trying to integrate over the region D, where D is this region here. This is D. Okay. And then now let's start converting things over. So what is the x over here? Again, we use r cosine theta. And then what is the y? We use r sine theta. So I'm just doing it by the book, so to speak, and then I'll show you a slightly faster way in a minute. And then dA here is the r dr d theta. Great. And then I have my bounds here that I'm going to figure out in a minute. Okay, so if I just simplify over here, I get r squared cosine squared plus r squared sine squared. Factor out the r squared, I get sine squared plus cosine squared, that's 1. I just get r squared. Okay, and that was, I'm going to mention now the easier way, because remember that r in polar coordinates is the square root of x squared plus y squared. So one of the nice things in polar coordinates, if you see an x squared plus y squared floating around somewhere, it converts to r squared. So that's really nice. So we have now simplified the integrand. It's r squared times r, so that is r cubed, dr d theta. So great. And now we're trying to find this region of integration. So how do I find this region of integration, or how do I convert it to polar coordinates? Well, remember, if I start at the origin and I draw my representative lines for my polar coordinates, right, then I'm trying to figure out what are the bounds for r. So it's pretty clear that r is going to range from 0 to whatever the boundary is of this region, which is the circle up here. So I'm going to have to convert this circle to polar coordinates, and that'll be my upper boundary for r. And my lower boundary for r is always going to be 0. So I'm going to put a 0 here, and then I'm going to go back up here and try to convert this to polar coordinates. How would I do that? Well, this gives me a good opportunity to tell you not to start here. I'm going to tell you instead to go back to the original representation of the cylinder. How come? Because there's, again, that magic x squared plus r squared, x squared plus y squared. That converts pretty easily right away to r squared in polar coordinates, right? That's what we said down here. And then the 2x here converts to 2 times r cosine theta. Okay, so from here you have two options. Either r is 0 or r is 2 cosine of theta. We definitely know that this curve and most of this region, with very few exceptions, is not the graph of r equals 0. That would not give us this region. So this is the portion of the conversion that we just did, which actually represents the circle that is the boundary of this region. And as we said earlier, r goes from 0 to the boundary, which is that circle. And now we have figured out what that boundary looks like in polar coordinates. So that's just 2 cosine theta. Great. Then we got to ask ourselves, thinking in terms of theta, I start here, and then I move a little bit, and then I'm over there. So theta is getting bigger. Theta is getting bigger. And then I kind of stop here. I don't move over here because there's no graph here. So actually, it looks like the largest that theta can be is pi over 2. And if I repeat this process, but I go the opposite way, if I start here and then I go this way, now I'm measuring theta negative, and then I'm measuring theta negative, measuring theta negative, and then I get here, which is negative pi over 2. If I keep going that way, there's no graph here. So the smallest that theta can be is minus pi over 2. So at this point, I have converted the integral pretty easily into, or I have obtained a fairly simple integral to integrate. So I'm going to work through that. So what is my region, or what is my integration work out to here? I'm just integrating r cubed. That gives me r to the 4th over 4, evaluated from 0 to 2 cosine of theta. And I get integral from minus pi over 2 to pi over 2, 2 to the 4th, which is 8 times 2, 16, and then divided by 4, so that's 4, and then I get a cosine to the 4th theta d theta. Okay, so another opportunity to remember some more of your trig identities, and then I will leave you to evaluate the rest of this integral. So what do I do with this cosine to the 4th? Well, this is cosine squared times cosine squared. And cosine squared has its own double angle identity, which is 1 plus cosine of 2 theta, all over 2. So I basically am integrating this 1 plus cosine of 2 theta all over 2 squared d theta. Great. So this 2 squared is going to give me a 4, cancel out with that 4. So I'm just going to write that. Then I get 1 plus cosine of 2 theta, all of it squared d theta. So what do I do now? Well, now I can square this out. And this is going to be 1 squared, which is 1, plus cosine theta, cosine of 2 theta times 1 times 2. So that is, we're doing the quick square here. And then plus cosine squared 2 theta. All of this d theta. This one I can integrate. That integrates to theta. This is just a cosine of 2 theta. That's a simple use substitution. What about this one? Well, that one we convert again to 1 plus cosine, in this case, of 4 theta. So we keep doubling the angle every time we use this double angle formula, all divided by 2. So, and once I do that, I'm going to be able to integrate 1/2 to 1/2 theta, and then this is another substitution. It's going to end up being sine of 4 theta all over 4 for that integral. Great. So at this point, we can now finish this off and then use fundamental theorem of calculus to work out everything. I will leave the details to you to show that you, in fact, get 3 pi over 2. And again, if we scroll back up to the very beginning of this problem, we were told, find the volume. So we are, in fact, finding a volume. It was not an easy volume to picture, so I tried my best to draw some pictures here. Many times it helps to use something like a calcplot 3D or some other graphing utility to help you visualize these things. But I've been avoiding that for these past few lessons because I've been trying to help you develop the skill of being able to take one of these prompts and specifically trying to sketch the region yourself so that you understand the region of integration. And then from that will flow the limits. And then you can, of course, do the integral. But it is helpful nonetheless to be able to visualize these things. And then again, the skill of sketching it, even if it's not perfect, clearly, is a very useful skill. So quick little review here of some fundamental aspects of what we've talked about. So if you are going to integrate in polar coordinates and you're doing double integrals, the area element is r dr d theta. So it is very easy to forget the r. That's a very simple mistake. Dx dy does not convert to just dr d theta. You really do need the r. The second thing to remember is that the x and the y get replaced with r cosine theta and r sine theta. And then after that, really it's just about trying to figure out how to express your region of integration in polar coordinates. And the one tip that I gave there, which happened in both of these examples, anytime you see an x squared plus y squared, that is literally r squared in polar coordinates. So that really helps a lot. Another reason, that's another reason why I said in this example, let's not start from here to try to find the polar coordinate version of this formula. You can see that if I had put in r cosine theta here and r sine theta, I would have gotten some big jumbled mess when I squared r cosine theta. Whereas going up to over here got me to very quickly, in just 2 lines, the equation of the boundary of this region D. And then that formed the upper bound for my r integral. Great, so that's all for this video, and I'll see you in the next one.